Okay, we look at the Heaviside function and some things it's good for. Heaviside function is equal to 0 up to where t equals 0, and it's equal to 1 forever thereafter. So there's your definition, and you probably ought to do this. It's kind of traditional. Okay? And here's the Laplace transform. Simple and straightforward as it can possibly be. I'm not even going to comment on it. Okay? Now, the Heaviside Laplace transform, the Heaviside function shifted to the right alpha units. That's this. We understand from pre-calculus how you shift and deal with graphs, and I went on a little while about pre-calculus ought to give you better visual skills for this, and then calculus ought to reinforce them a little bit, so when you get to differential equations, you can just answer these questions very quickly. But we know it's not true, so we drag this out of you. But that's okay, because it actually worked pretty well. I think you understand it. Because when you finally saw what we did here, you both wanted, you know, kind of the old kick yourself thing, how did I not see that? So, you know, you're okay. Okay, well, anyhow, well, here's the integral you get for this one. It's very straightforward. If you shift the Heaviside function alpha units to the right, you get a Laplace transform of that function is 1 over s e to the negative alpha s. Okay, so there's a picture. There's the transform. Now, what we want is, our goal was to find this purple function. Okay? Now, here's the answer, but you know, we had to go through a process to figure this out. Okay? Well, we figured out that if you take a shifted Heaviside function, shifted by alpha, there's your h of t minus alpha, gives you this green function. We still don't have the purple function. What we have to do to get the purple graph is we have to have this, which is just the Heaviside function shifted beta units with a negative sign in front of it, which is where everybody went, oh, darn. Okay? So I think you see that now. And if we do that, well, then we've got this function at 0 everywhere, but on this interval. Okay? So our f of t function, if this is our f of t function, is h of t minus alpha minus h of t minus beta. What's its transform? Plus transform is just 1 over s e to the negative alpha s, because that's a transform of t, h of t minus alpha, minus transform of h of t minus beta, which is 1 over s e to the negative beta s. Okay? So we get 1 over s e to the negative alpha s minus e to the negative beta s. And that can be useful if you have a differential equation where you pulse energy into it or whatever, you know, whether it's a rotating system or a spring mass dashpot system, or an RLC circuit, or a more complex circuit. If you pulse energy into it here, you know, a force or a voltage, you can solve the differential equation. And that's not a nice function that you can just integrate. I mean, it is, but you can't plug that in as a trial solution in your differential equation. Try it and you'll see. Okay? It doesn't have a nice functional representation. Okay? So what you want to do is you want to take your equation and very easily transform it over to Laplace transform space, solve the equation in Laplace transform space, then bring it back into the real world and see what your system's going to do. Okay? Well, even more importantly, if you have a step function, how are you going to do that? Well, take us a little while. Okay? And what you have to see is, okay, if you just do your h of t function, well, it's like this, right? Now, if you subtract h of t minus 1/2, you're going to have this and this, right? Then if you add h of t minus 1, you're going to have this, but then of course it's going to continue on here, right? And then you subtract h of t minus 3/2, and now you're going to have this, 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 and this, and of course it just keeps running on here. Okay, so we kind of illustrated that. The pictures probably won't make much sense on a video, but we just keep shifting 1/2 unit and alternately adding and subtracting Heaviside functions. And if you understand the visual, and I think you do well enough to at least go home and work this out and convince yourself that it really works, you see you have something like this. F of t is h of t minus h of t minus 1/2 plus h of t minus 1, and then h of t minus 3/2 and h of t minus 2, alternately adding and subtracting, moving a 1/2 unit every time we build this function. So we just put 3 dots on it. That's what it does. What's its Laplace transform? Well, that's easy. If you just use this, and this is easy to get, okay? But, you know, it's several easy things that get put together into something that's not all that hard, but not as easy as the easy steps, okay? So we get the Laplace transform, we just write it down. It's, and we wrote down Laplace transforms for, you know, the Heaviside function, then minus the Heaviside function shifted 1/2 unit, and then the Heaviside function shifted 1 unit. Well, we just do the same down here, now that we've got a good explicit picture of our function. Factor out the 1/s, and notice, and the thing you have to notice is that if you square e to the negative 1/2, you get e to the negative 1, right? Or square e to the negative 1/2 s, you get e to the negative s. If you cube e to the negative 1/2 s, e to the negative 1/2 s raised to the third is e to the 3 times negative 1/2 s, right? And we get this. And it just continues, so we can write this as 1/s times r to the 0 minus r plus r squared minus r cubed plus r to the 4th and so forth, where r is your e to the negative 1/2 s. Might be a little hard to read. Okay? And then you would immediately recognize this as a geometric series. If anybody knew anything about geometric series, even after a calculus course, and if you don't, you need to totally understand geometric series at the level of pre-calculus. Okay? So put that on your list of things that are really important. Okay? Geometric series. Be able to prove the convergence of a geometric series. Okay? Well, an infinite geometric series converges, you know, the r to 0 and so forth. And, you know, I actually had a mistake up here. R should be negative 1/2 s, that'd be r to 0 plus r squared plus r cubed and so forth. Okay? If r is this, then it's 1/s times r to 0 plus r to the 1 plus r to the 2 and so forth. We don't need the alternating. Okay? So that when we do 1 minus r, it's 1 minus negative e to the 1/2 s if we want plus e to the negative 1/2 s. And again now, if you're driving a mechanical or electrical system with a step function, which happens, okay, it's like you close the switch and you get a pulse. You open the switch, close the switch, open the switch. Very easy thing to do. One of the easiest things to generate. Then you have the differential equation for the, you know, y double prime and the drag force on the y prime and the linear restoring force on the y, or the analog in an RLC circuit, which we haven't demonstrated here, but we've demonstrated a rotational system in harmonic motion. If you set that equal to the step function, you can't write its integral, okay? You can't use it as a trial function. You can't, because you can't find its derivative in any closed form. But you can translate the equation into Laplace transform space. And right there's the Laplace transform of your non-homogeneous step function that's driving the system. And you can then do the partial fractions and all the stuff to do the algebra to solve the system in Laplace transform space, and then bring it back to the real world and see what your solution looks like. Okay? So, very powerful. So that's a big deal. Okay, well, we want to go on with it because there are other functions that we can generate. So we're just going to throw out the question of how we would generate function that does this, or maybe a sawtooth. Okay? And that involves just basing it on a step function, but multiplying the step function by some linear function. Okay? So you got to find the proper linear function, or the linear function allows you to do this. So think about that one.